right. හරි පුතේ. එතකොට අපි paper discussion 2 එක paper 5 එකේ paper discussion 2 එකනේ second paper එක කතා කරන්නේ. right. හරි බලන්න. එහෙනම් බලන්න එක. right. අද පොඩ්ඩක් මේ උණ සීන් එකක් තියෙනවා හොඳේ. වැඩි පොඩ්ඩක් අමාරු නොතින් පොඩ්ඩක් කලින් නතර කරනවා. බලමු නේ. තියෙන විදිහට තමයි. right. බලන්න පළවෙනි එක. Microorganisms are widely used in industry because they efficiently convert cheaper raw materials into more valuable products. Two. Name two types of microorganisms used in industry. So the two type of microorganisms used in industry කිව්වම පස්සේ ඕකේ බලන්න ටියුට් එකේ දීලා ඇති ඉන්ඩස්ට්‍රි එකේ යූස් කරන මයික්‍රෝගනිසම්ස් ලා single protein producing microorganisms ඊට පස්සේ තා මොනවාද microorganisms that are used which produce like microorganisms like which are the end products of microbial actions, like depending on the end product of the microbial actions, depending on the like the byproduct of the microbial actions, and single protein cell microorganisms. Likewise, few of the different like mostly in the food industry, as I remember, were given. Name two type of microorganisms used in industry. Yeast in alcohol production, sort of. Then lactose in dairy production. Those sort of answers are correct. Like if you like answered any of those ones, then that is correct. Second one, name two industries that convert cheap raw materials into valuable products. So like dairy industry, you produce cheese and all, right? And what else? Compost, right? Compost is also one of the industries that you convert cheaper raw materials into valuable ones, because like organic, like this compost is organic fertilizer, right? So likewise, the next one, name two. Okay, third one. The diagram below shows a typical process for treating industrial wastewater. Name the cases labeled A, B, C, D, right? So A is primary treatment tank, right? A is primary treatment tank. A is primary treatment tank. Primary treatment tank. A is primary treatment tank. Oh, you can call it sedimentation tank as well. Primary treatment tank. Then the B is what? B is secondary treatment tank, right? B is secondary treatment tank. B is secondary treatment tank. And C is what do you call C? Biogas reactor, right? Oh, biogas reactor, C, right? Right. So those are the A, B parts. And D is D. D. is what? This is tertiary treatment tank it should be, because this is where you put like all the disinfectants there, right? The secondary, then tertiary disinfectants, then to the natural ponds, right? We call this digester tank as well. Digester tank. Digester tank as well. So this is what uh, tertiary, right? Tertiary treatment tank. Tertiary treatment tank. Tertiary treatment. Right. Fourth question. Name the cases where microorganisms are used in the above process and explain how. So the microorganisms are basically used in where? In the treatment, like the primary treatment, microorganisms aren't used, but in the secondary treatment, yes, the microorganisms are used. And in the digester tank, the microorganisms are again used, right? So there's only like two of the places where the microorganisms are used. One is microorganisms are used in our process, right? So in the first case, this in the secondary treatment plant, secondary treatment plant, microorganisms are used, right? And explain how. The secondary treatment plant, what happens there is like aerobic microorganisms, right? Aerobic microorganisms, microorganisms convert organic matter, organic matter into organic matter into carbon dioxide plus water, right? Carbon dioxide plus water. And the second place where the microorganisms are used is the digester tank, right? It's the digester tank. It's digester tank. So in the digester tank happens there. In the digester tank, methanogenic bacteria are producing methane gas using the organic matter, right? So it's basically methanogenic bacteria or methane producing bacteria. Methanogenic bacteria, right, are producing are producing are producing methanogenic bacteria are producing methane gas, right? Methanogenic bacteria are producing methane gas using the organic matter. Organic matter. And it should be anaerobic respiration as well. So anaerobic AE, anaerobic respiration. In anaerobic respiration. Right. Fifth question. Biogas occupies as a prominent place among the alternative energy sources used as a solution to the energy crisis that has affected all countries of the world. Name the four stages that comprise biogas production process. So the biogas production process completely happens in three steps. What are the three steps? So first one is hydrolysis. First one is hydrolysis of the organic matter. Hydrolysis. Second step is fermentation, right? Second step is fermentation. Then the third step is fermentation, acetic acid production, right? It's acetic acid production. It's acetic acid production. And the last one is methane production, right? Last one is methane production. So those are the 4 steps in biogas production, right? Part B. Proteins are polypeptide chains formed by the polymerization of alpha amino acids of the following, right? So this is an alpha amino acid. Proteins are polymerization of this alpha amino acid. First question: what are the special names given to A and B in the above structure? This is A, this is B. So A is amine group, the amine group, and B is carboxylic acid, right? Carboxylic carboxylic acid. The first one is a amine group. Second one is carboxylic acid group. Those are the 2 groups, A and B. Just move. 2. Name the simplest amino acid and draw its structure. So we know we know the structure of 5 of the amino acids. We named it GAPSA: glycine, alanine, phenylalanine, cysteine, and aspartate. Right? Those are the 5 amino acids we know, and the simplest one is the first one, which is glycine. And this is simple because the structure of this, like the amino acids change to each other because of the R group, right? When the R group of the amino acid changes, complete amino acid changes. So like in the simplest form, this R is a hydrogen group. That's all, right? In the simplest form of amino acid, this R is a hydrogen group. And like this is, you have to remember, when the R group changes, the amino acid completely changes, and likewise there are like 20 amino acids. Out of that, the simplest form of amino acid is when the R group is a hydrogen, right? We have to draw an amino acid which has a hydrogen as the R group, right? So rest of the other things are same. COOH, here it's NH2, right? Everything are same. So then I have to label it. This is carbonyl carbon, alpha carbon. Asking for that, this is enough. How can alpha amino acid be identified? What is alpha amino acid? Alpha amino acid is something like this. Now this carbon is called what? This carbon is called carbonyl carbon. Carbon is called carbonyl carbon. The carbon next to this carbonyl carbon is called alpha carbon. This is carbonyl carbon. The carbon next to this carbon is alpha carbon. And if an amine group is attached to alpha carbon, that is called an alpha amino acid. We will write it. Now C double bond O carbon in carboxylic acid carboxylic acid, the double bond O carbon in carboxylic acid is called carbonyl carbon is called carbonyl carbon carbonyl carbon, and the carbon next to carbonyl carbon, right? The carbon next to carbonyl carbon is called alpha carbon, is called alpha carbon. And if an amino group an amino group is attached to alpha carbon, an amino group is attached to alpha carbon, is known as alpha amino acid. Is known as alpha amino acid, right? Write a way to change the function of protein in three-dimensional space. Write a way to change this function in the protein in three-dimensional space. So if it is a protein in three-dimensional space, what you can simply do is like change its structure. So if you change the structure, it will completely change its function. So as we discussed like before, can you remember I said like proteins are like tractors. Like tractor has a shape, a structure which can do a function, right? The tractors have shapes or the structures which can do a function. So like they have wheels, they have steering wheels, and they have seats, they have an engine, everything is there, right? That is necessary. All those are structures. And if you change that structure, like depending on that structure, it does a function, right? If you change that structure, now the tractor will do something completely else, different. So now that is what simply we have to do with the protein, because protein is a structure as well. So because of the structure, it has a function. So if you want to change the function, what you have to do is actually you change the structure. That's all. Write a way to change the function of a protein in three-dimensional space. Change the protein structure in the protein structure by an acid base, which means like basically you change the pH or changing salinity, then temperature. If you change any of those, the structure of the protein will change, and it will change the function as well, right? Among the structural forms of proteins, there are two main forms of secondary structure. So now this is a bit out of the syllabus, because like this one is like the old syllabus thing, which like there was two of the structures in the secondary protein type, alpha helix and beta plated sheet. It's now out of the syllabus. It's not there in the syllabus now. Now there are like three of the proteins that we learned. So we'll change the question a bit. among the structural among forms of proteins. The three main types of there are three main forms of structure. What are they? Right. There are three main type of structures in protein in the new syllabus now. One is fibrous proteins. Fibrous proteins. Fibrous protein. Second is fibrous proteins. Second is globular proteins. Globular proteins. And is globular protein. Then the third is actually globular proteins, and the third is actually fibrous proteins, globular proteins. Then the third is actually hybrid proteins or the complex hybrid proteins. Complex hybrid proteins. Complex hybrid protein. Complex hybrid proteins are the three main type of proteins. Next question 6. What are the three factors that affect the activity of an enzyme? Three factors that affect the activity of an enzyme. Are these like the factors affecting the proteins? What are these? Temperature, then pH value, then the salinity, 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 and enzyme inhibitors. Enzyme inhibitors, right? Enzyme inhibitors. Enzyme inhibitors. 7. What are the enzyme inhibitors? Enzyme inhibitors are the organic or inorganic particles. They can be organic as well. Mostly they are inorganic. Organic or inorganic particles that attach to the enzyme, right? That attach to the enzyme and changes its active site or changes its structure to inhibit its function, right? Changes its structure to inhibit its function. Enzyme inhibitors are enzyme inhibitors are inhibitors are organic or inorganic structures, organic or inorganic structures, organic or inorganic structures. Enzyme inhibitors are organic or inorganic structures. They're mostly inorganic structures. Attach to the enzyme to change its structure to inhibit the activity of enzyme, right? To inhibit the activity of, right? Which hormone is used to control diabetes? That is insulin, right? Is insulin. That is insulin. Insulin is insulin. What solution is used to detect the presence of protein in egg white? What solution is used to detect the presence of protein in egg white? What color can be observed at the end of the day? The protein detection solution. What solution is used to detect the presence of protein? Is biurate, right? Biurate. Biurate solution. And the color change they asking, right? What color can be observed at the end of the purplish blue? The purplish blue. Purplish blue color. Mention the four main steps in soap production. So it's saponification, then uh, what? Then the uh, removal of what? This glycerin, removal of glycerin. Then third step is to isolate soap or concentrate soap, and then fourth is to hold on for a second. Well, exactly what they are. Soap production comes under soap. So yeah, saponification, removing of glycerin, soap refining, uh, making into finish soap. Right, four steps in products or production. The first one is what? First one is saponification. Saponification is first one. Saponification. Removing by doing the byproduct glycerin. Right. Removing the byproduct glycerin. And the byproduct glycerin. Third one, soap refining. Right. Soap refining. Soap refining. Last one, making into finished soap, like adding additives and sort of like everything to final finish soap. Finish soap. The reaction involved in the production of soap is shown below. This is saponification reaction. This is basically the soap. This is glycerin. This is sodium hydroxide, and this is triglycerides or the oils. Name the compound A, B, C above. A is caustic soda, or sodium hydroxide, right? Sodium hydroxide. Sodium hydroxide. Sodium hydroxide. B is what? B is glycerin, right? Glycerin. B is glycerin. Is C. C is a triglyceride. Triglyceride. B is a triglyceride. Right. What chemical compound is used instead of NaOH, sodium hydroxide, to make a mild soap? Right. What chemical compound is used instead of NaOH to produce a mild soap. That is KOH, right? KOH is used as for the like Angigana Sabang wage scene, right? Second, the following is an experiment set up by students studying a technical subject to demonstrate the principle used to produce acetylene, C2H2 gas. So they are producing C2H2 gas, which is required for gas welding. Acetylene is basically used for welding, right? Oxyacetylene gas. The chemical reaction that occurs in the above system is shown below. So this is the chemical reaction. This is calcium carbide reacting with water, producing calcium hydroxide and acetylene gas. So it was observed that the container heated up as the reaction occurred, which means it should be a exothermic reaction, right? It should be exothermic reaction. But is the above reaction exothermic or endothermic? So as the container heated, which means the heat is released, so therefore it's a exothermic reaction. The exothermic reaction. B. Rewrite the balanced chemical equation for the above chemical reactions. Write the balance equation. CaC2 plus H2O converts into calcium hydroxide plus C2H2. So that's what's given. They are balances. Calcium to calcium balanced. Then two of the carbon are balanced. Then hydrogen, two hydrogens are here. There are like 2 hydrogen plus 2 is 4 hydrogens are there. So if you put a 2 here, now the hydrogens are balanced. Now 4 hydrogens are there, and oxygens last to balance is like 2 here. There's 2 here, so it's balanced, right? You just have to put a 2 here. This is the balance equation. Right. 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 Come to the next one. Draw the energy diagram for this reaction. So if I draw energy diagram, y and x-axis, y should be energy and the x should be reaction progress. Right? Reaction progress should be reaction progress. So the reactants are acetylene and carbide and water, right? And since it is an exothermic reaction, energy is released. Therefore, the energy of the product should be low. Energy of the reactant should be high. So the reactants high, product energy low. High reactant energy, low product energy. So the reactants were C2, CaC2, right? CaC2, calcium carbide. Reactants were C2 plus H2O, and they converts into what? CaOH twice plus CaOH twice plus C2H2. They converts into CaOH twice plus C2H2. The reaction has a jump, and this is activation energy EA. Activation energy. And if you want to write, this is the heat of reaction. This is transitional state. That is all to label if you label it. Transitional state. It's own label can that is all to label. Okay, label it. Transitional state. Okay. Right. The chemical compounds indicated by A, B, and C in the above diagram. A, B, C, A, B. Now, A should be calcium carbide, the solid. B should be water. Then the calcium carbide and water are mixing. Then the C2H2 is produced and it's released as C. Right? So A calcium carbide, B water, C acetylene or C2H2. Yeah. A is calcium carbide. B is water H2O. C is acetylene gas C2H2. Write down a measure that can be taken to increase the rate of above reaction. So to increase the rate of reaction, you can either heat it, or the best thing is you put the calcium carbide in powder form. So if you put it in powder form, the surface area will increase. Therefore, the rate of reaction will increase, right? What will happen? So put the calcium carbide in powder form. Powder form. If it is found that the concentration of calcium hydroxide increased by 0.12 moles per cubic decimeter, calculate the average rate of reaction. Sorry, average rate of formation of calcium hydroxide. Now, average rate of formation, like average, if it is average rate, the stoichiometry should be reciprocal before the rate of reaction, right? So, like, I write it like this: RTaOH twice. So this should be a production rate. Therefore, it doesn't have to be minus. It's a plus value. Now we have to check the stoichiometry of it. It's just 1. So nothing to worry about. It's just 1. The concentration difference of calcium hydroxide, right, over time difference. So this happens in how many seconds? It found that the concentration of calcium hydroxide increased by 0.12 moles per decimeter. Calculate the average rate of formation of. And now the issue is time isn't given. Ne? Reaction එක උඩ මොනවා equation එකේ time එකක් ගැන කියලා තියෙනවා. Following is experiment set by students studying technical subject to demonstrate the principle used to produce green gas which is required for gas welding. No. Time එකක් කියලා නැහැ නේ. ඉතින් අපි ඒක 1 second කියලා අරගෙන ලියමු. It's found that the concentration of calcium hydroxide increased by 0.12 mole per cubic decimeter. Calculate the average rate of formation of calcium oxide. We'll take it as 1 second. So it's 0.12 mole per decimeter. The final initial is 0. So take the time as 1 second because it's not given. 0.12 mole per decimeter per second is the rate of reaction. The rate of reaction. D. The uses of C2H2 can accelerate the ripening of fruit. That is true. Like because this is one of the plant hormones, acetylene. Right? Explain the function of C2H2 here. C2H2 is a plant hormone responsible plant hormone responsible for the ripening of fruit. What it basically does is it hydrolyzes the pectin. It hydrolyzes the pectin because the pectin is the polymer that like keeps the cells attached strongly together. So when the pectin is hydrolyzed, it's becoming soft. Think of a guava fruit. If you like bite it when it is raw, really hard to bite. But when it's ripening, what actually happens is the pectin that is there, like which is tightly holding the cells in the guava fruit, is hydrolyzed, so the cells are becoming more soft, so you can easily bite it. That's what actually happens. Right. Briefly explain what would happen if tube X was immersed in water. Tube X is like the one tube which is there to remove acetylene gas. So if it was immersed in the water, the water level will go up, right? The water level will go up because if you think about it, like if you put like tube here and sort of a gas is accumulating around here, so this gas pressure increases. It push the water level downwards, therefore the water rises up and outflows through the tube X, right? Accumulated C2H2 increases the pressure. Therefore, the water level goes up and outflows through tube outflows through tube X. That's what happens. The data for the experiment to experimentally determine the heat of reaction of the acid-base reaction that occurs in 2 moles per cubic decimeter. 2 moles per cubic decimeter HCl. 50 cubic centimeter, 2 mole per 2 mole cubic decimeter KOH, then 50 cubic centimeter HCl and KOH are given below. So those are the temperatures and the concentration. And temperature of the initial KOH solution is 30. Temperature of the initial HCl solution is also 30. Maximum temperature of the mixture is 42. That may be the final temperature. Density of the water is 1 gram per cubic centimeter and specific heat capacity is this much. Right? What is the mass of the mixture? So you are given the density. So basically, this is what happens, right? So there's KOH in a beaker, let's say. There's 2m, 2m. 2m means 2 moles per cubic decimeter. 2m KOH in this beaker, and that is how much? 50 cubic centimeters, right? That is 50 cubic centimeters of 2m is there, and you add another 50 cubic centimeter of HCl into it. 2m HCl, another 50 cubic centimeter is added to it, and these two will react with the container. So what is the mass of the mixture? What is the mass of the mixture? So the mixture volume will be 100 cubic centimeters, right? The mixture volume will be 100 cubic centimeters, and what you put there is Q equals mc theta. Q equals mc theta. So how do you find the mass before putting mc theta? Mass is density into volume, right? Because density equals mass over volume, d equals m over v. Now the mass should equal to d into v, dv. So density is 1 gram per cubic centimeter, and the volume of the whole mixture is 100 cubic centimeter. Now there are 100 grams of it. There are 100 grams of it. The mass is actually 100 grams. Specific heat capacity is 4.2, and it says the final temperature is 42 degrees from 30 degrees, that is 12 degrees of a temperature difference, right? I'm sorry, what is the mass of the mixture they're asking? So answer was already given here. Mass is this. I don't have to calculate this in here. Probably the questions are asked now down somewhere. State an assumption you have made here. So what is the assumption we have made here? So we took the density of the water here, didn't we? We took the density of the water here, and now we took it as the density of the water should equal to the density of the mixture, right? We took the density of the water is equal to the density of the mixture. So density of the water is equal to density of water is equal to density of the mixture That was the assumption. What is the temperature change given, right? 42 minus 30 degrees of Celsius, which is 12 degrees of Celsius, right? Calculate the heat change that occurred in the reaction. Now that is where we take Q equals mc theta. Now we know the mass, 100 grams, and the specific heat capacity in grams is 4.2, which difference is 12. So you have to multiply this. So 4.2, 12 into 100, right? So it's 100 into 4.2 into 12, 5040 joules, right? 5042 joules, right? 5042 joules. What assumptions are made in calculating the heat change above? In the heat change above, we assume that heat is not wasted to the environment, or the container does not absorb any of the heat, right? Container does not absorb any of the heat, and container does not absorb any of the heat, container, and none of the heat was wasted to the environment. Right? Right. Fourth question. On heating a block of ice at minus 10 degrees to water at 100 degrees of Celsius, draw the changing in temperature of matter in the presence of heat, the graph below. It starts minus 10 degrees of Celsius, then goes up to 0 degrees of Celsius. This is MC theta. Therefore, the temperature is changing. So, when it comes to the 0 degrees of Celsius, now it is latent heat. In the latent heat, the temperature isn't changing, so it's a constant. Now, after the constant, again the temperature increases, right, until it becomes 100 degrees of Celsius, right? Until it becomes 100 degrees of Celsius, the temperature increases. Afterward, after the 100 degrees of Celsius, it again becomes constant, right? So this is called a heat curve. So this is 0 degrees of Celsius. This is 0 degrees Celsius ice, right? And at this point, it all converts to 0 degrees of Celsius water. It all converts to 0 degrees of Celsius water. And at this point, it's 100 degrees Celsius of water. At this point, it all converts into 100 degrees of Celsius steam, right? You apply MC theta here, ML here, MC theta here, ML here. You don't have to label those. Okay. Next one, third one. 3 instruments used to take measurements in the laboratory are shown below, right? So these are the instruments used in the laboratory. Take the measurements. So the first one is vernier, second one is micrometer screw gauge, third one is a traveling microscope. Name the measuring instrument. A is a vernier caliper. B is the micrometer screw gauge. Micrometer screw gauge. C is a traveling microscope. Name the parts of the following apparatus. Following apparatus. Okay, P. Outer jaws. Is outer jaws. These outer jaws. Then R. I'm sorry, P are the inner jaws. P are the inner jaws. These are inner jaws. P are inner jaws. Right. P are the inner jaws. They are the inner jaws. R are the outer jaws. Right. R are the outer jaws. Outer jaws. R are the outer jaws. And then the T is the vernier scale. Is the vernier scale. The vernier scale. And U is the main scale, right? U is the main scale, right? U is the main scale. There's V as well, but V isn't given. V is the depth probe, right? It's the depth probe. V is the depth probe, right? When part X is moved, indicate the parts that move with it. Part X. So when the part X is moved, one inner jaw is moving, one outer jaw is moving, and the probe is moving, the vernier is moving. So when the part X is moved, indicate the parts that move. One inner jaw, right? One inner jaw, one outer jaw, right? one outer job, then one inner job, one outer job, depth probe, and the vernier scale. Right? Those are the parts. Oh, three readings obtained from the diameter of a circular plate in an experiment are shown below. Which part of the instrument was used to obtain the above measurements? Diameter, it's diameter. Sorry. Three readings obtained for the diameter of a circular plate. So diameter is like circular plate, solid. The external diameter. Three readings obtained for the diameter of a circular plate. So its plate is a solid one, not hollow. So like outer diameter, right? Outer jaws. Outer jaws, right? Calculate the average value of the above three measurements. Add them together, divided by 3. Add them together, 70 plus 70.6. 70.6 plus 70.4 plus 70.2. You divide it by 3. Is 70.4, right? How do you calculate the average? You add them all together. Then you divide it by the number of times. That is 70.4, the final answer, right? Millimeters. Okay. When the jaws of the above instrument are in contact with each other, the scale is shown below, right? So this is the scale when the jaws are in contact, right? Jaws of the above instrument are in contact with each other, the scale is shown below, right? This is how the scale is when the jaws are in contact, right? The main scale, this is the vernier scale. What is the smallest measurement of the instrument? So it's 10 verniers, 9 main scale divisions. It should be 0. I think we better show it calculated. So LC equals, write the whole thing. LC equals 1 MSD minus 1 VSD, obviously. So 1 MSD is 1 millimeter. Okay. 9 is coinciding with 9, sorry, 10. Come 0.1 millimeter. So the whole thing shows you no marks. 2. What is the zero error of the device? There's a zero error. See, the two of the zeros are not aligned. This is a negative zero error because the zero of the vernier is behind the main scale 0. So it's a negative zero error. In case of negative zero errors, you don't measure it like the normal way. Instead, you deduct the number of aligning vernier lines by the number of vernier scale lines, which is 10. So 10 minus aligning number of vernier scale lines into the least count with the error. So which line is aligning now? 1, 2, 3, 4. This 4 is aligning, right? 4 is aligning, which means you have to take 10 minus 4. Zero error is 0.1 millimeter into 10 minus 4, which is 0.6 millimeters, right? 0.6 millimeters. What is the average value of the correct diameter? Now this is sorry, you have to put negative here because it's a negative zero error. You have to add them all. Average value of the correct to find the average value of the correct diameter, you have to add them all and deduct it by 3 again. Sorry, divide it by 3 again. I have to add them all again. 70.6 plus 0.6. 70.6 plus 0.6. is 71.2. 71.2. That is 71.2 plus 70.4 plus 0.6, 70.4 plus 0.6 is 71, and then 70.2 plus 0.6, which is 70.8. So you divide it by 3, the whole thing by 3, so that should be 71.2 plus 71 plus 70.8. That is 213 altogether. 213 divided by 3 is 71 millimeters. What is the fractional error of the measurement? So fractional error is what? Fractional error equals error over measurement to no, the 100%. If you take 100%, that will be percentage error. Take fractional error, it's 0.6 millimeters of error divided by the measurement is 1. You don't have to simplify it in decimals. Fraction error, you keep it as a fraction. It was found that when the temperature of the existing circular plate was increased by 85 degrees, the new diameter obtained was 71 millimeter. Okay. Already 71 for us. Okay, anyways, it says it was found that when the temperature of the existing circular plate was increased by 85 degrees of Celsius, new diameter obtained was 71 millimeters. Therefore, calculate the linear expansion of the material from which the plate is made. Issue. Because this is the original length, and even after 85 degrees of temperature increase, it's still 71. So nothing has increased. Sort of error there, right? Hold on for a second. හරිද අපිට ආවා plus 71 point 71 plus 70.8 71 70.8 divided by 3. What? So like they're supposed to be at least sort of like bit of an increase in the length, isn't it? Maybe they calculated without the correction, so we take the very first length we measure. Very first 70.4. We'll have to take this. If we take 70.4 as the length, so it has increased up to 70. So the delta L, right? Delta L is 71 minus 70.4 because this is like before correcting the error, right? So that is 0.6 millimeters. This is the amount of length that has expanded. If I put delta L equals L naught alpha delta theta. L naught is the initial length, which is 70.4. And find alpha. Find alpha. And find alpha, and the temperature difference is given. Increase by 85 degrees of Celsius. Is by 85. So alpha should equal to delta L is 0.6. 0.6 divided by 70.4 into 85. 0.6 divided by 70.4 divided by 85. That is how many cells? 1, 2, 3, 4. 1.0026 into 1, 2, 4, 10 to the power minus 4 per Kelvin is the alpha, right? How we calculate the alpha using the linear expansion, right? 4. The figure above shows a setup prepared to experimentally determine the specific heat capacity of coconut oil using the mixture method. So we are going to find the specific heat capacity of coconut oil using the mixture method. Right. So the figure above shows a setup prepared to experimentally determine the specific heat capacity of coconut oil using the mixture method, right? So a thermometer is there The stir is there, coconut oil is there, then the thermal insulating metals are kept there, chilled coconut oil is there. Coconut oil. Write the measurements to be obtained here in order. So now this is mixture method. So you mix two of the uh, oils here. Above shows a setup prepared to experimentally determine the specific heat capacity of coconut oil using the mixture method. In case of this, he is supposed to know the who is releasing the heat and who's absorbing the heat. Obviously, I think the coconut oil is absorbing the heat. The question doesn't give what is releasing the heat. Thermal insulating materials are there. Okay. Thermometer. Good. Write the measurements to be obtained here in order. 1 M2 M3. So M1 M so liquid 1, liquid 2, initial temperature of the, let's say liquid 1, initial temperature of the liquid 2, final temperature of the mixture, and the final mass of the mixture should be the things. But the doubt is, what do you mix it with? Right, the equipment used for the above measurement. Hold on. Hmm. Okay. Now, in this case, some sort of a liquid should release the heat. The other liquid should absorb the heat, because to find the specific heat capacity of coconut oil, you can put the energy release is equal to the energy absorbed by the coconut oil, and the energy release by the other oil uh, can be calculated using Q equals mc theta. So to put mc theta, supposed to know C, the specific heat capacity should be known. Otherwise, you can put it in Right. So anyways, we'll have to take one of another liquid, because if we take the specific heat capacity, like if we take both the liquids are coconut oils, take it here. We actually can take it that way, right? Yeah. Can actually take it that way. So both the liquids are coconut oil, because the container is also adding. So if the container is adding, the specific heat capacities won't cancel out. So my idea was this: if heat was released by the coconut oil here, is the, let's say, hot coconut oil, that is mc theta, and c is the specific heat capacity of hot coconut oil, equals the mc theta of chilled coconut oil. So the specific heat capacities are equal, they cancel out. But if the C theta of the container is adding, you can't just cancel out like this. They had to simplify it. So yeah. You don't have to like put a different liquid here, and use the same liquid. Like this is hot for the room temperature coconut oil, that is chilled coconut oil. So we'll take it that way. So you need to put in the complete uh, formula will be heat released by coconut water, sorry, not water, coconut oil plus container. Container is also releasing the heat. Coconut oil plus container is equal to heat absorbed by heat absorbed by the chilled coconut oil. So this is a bit confusing, and it's a good question, because like the very beginning it was confusing, because how two of the liquids that are mixing be the same to find the specific heat capacity of it. Now you actually can, right? So it's heat absorbed by chilled coconut oil. Now you can actually coconut. Coconut. Cocoa. Right. Right. Okay, now it's here. So M1 we can take as just coconut oil mass, and the other mass should be coconut oil plus. We have to have like 3 of the masses here. Now, yeah, coconut oil, and the M2 is chilled coconut oil. That's chilled coconut oil. Temperature of container and coconut oil, or the temperature of container and coconut oil. Temperature of container and coconut oil. Then the theta 2 is temperature of chilled coconut oil. Temperature of chilled coconut oil. Temperature of chilled coconut oil. And theta 3 is what? Theta 3 is temperature of the mixture. It should be final temperature of the mixture. Final temperature of the mixture, which is the equilibrium of temperature of equilibrium. Right? It is the temperature of equilibrium. M3 is the mass of container. Mass of container. Mass of container. Right. Have it all. Right. The equipments using this above measurements. So measure the mass, triple beam balance, okay, or the electric balance. Electric balance is okay. Electric balance, right? Temperature thermometer, thermometer, thermometer. Okay. Using the above measurement symbols, write an expression to find C, taking the specific heat capacity of coconut oil as simple C. Right? Also take the specific heat capacity of material from which the calorimeter is made as Cc. The mass of one is not right. So M1 C into the temperature difference. Was it given? Temperature difference? Theta 3 is the equilibrium. This is theta 1 is contained and normal. So theta 3 minus theta 1, right? Plus container is also releasing. So the mass of container M3, the bottom mass of the container is M3 here, into its specific heat capacity was taken Cc. This temperature difference is again theta 3 minus theta 1 because the initial temperature of both the coconut oil and the container is theta 1, right? So this is absorbed by the chilled coconut oil, which is the mass is M2. Specific heat capacity is same as the hot coconut oil Cc. Its temperature difference is, its original temperature is theta. I'm sorry, this should be the other way around because the temperature of these two is actually going down, isn't it? Because this is, you are putting chilled coconut oil, so the coconut oil inside the container and the container's temperature should go down because you are adding chilled coconut oil, which means this should be theta 1 minus theta 3. 1 minus theta minus theta. This is 1 minus 3 and this is minus 3 as well. Because this is greater, this is less. The temperature difference of the chilled coconut oil, theta 3 here, is the final temperature. Theta 3 minus, because theta 3 is high, because the chilled coconut oil is absorbing heat. Theta 3 is high, its initial temperature is theta 2. Theta 3 minus theta 2. This should be the expression. A good question, actually. Should be the good expression, right? There's an assumption you made here. The heat released. Sorry. An assumption is like the environment didn't absorb any of the heat, or there's no heat waste to the environment. Is one of assumption made here because we equaled the heat released by the container and the hot coconut oil is equal to heat absorbed by the chilled coconut oil, right? Set an assumption you made here. The assumption is the heat is not wasted to the pipe. Is this method suitable for finding the specific heat capacity of a liquid like water? So, if you use water, right, what could happen? We are mixing two of the waters, that is here hot and chilled, right? Is this method suitable for finding the specific heat capacity of a liquid like water? C is a bit high. This is the thing. Specific issue is this, like, try to understand this. Specific heat capacity of water is really high. Get it? Specific heat capacity of water is really high. Therefore, it contains a lot of heat, but its temperature uh, change is very less. Get it? For a lot of heat transferred, it only increases a very bit of temperature because it has a high capacity of heat. The temperature change is very less. Therefore, if you add like chilling and with room temperature or normal temperature water together, because of the specific heat capacity, high specific heat capacity, temperature won't go high, or the temperature won't change much that you can observe, right? So the observation of temperature will be really difficult to use water. Like uh, if you try to find the specific heat capacity of water in this method, the temperature change won't be noticeable. Sort of a issue is there. I hope you understand that, because the specific heat capacity is really high. Now it won't change the temperature much. If you mix two of these liquids, it will change a little bit of temperature. That little bit of change of temperature is hard to notice. So not the best method. Anything else? Anything else? Why water is not the best? To like why this method is not best for the water? What else? The humidity, because it humidifies. Yeah, even you can take the humidity, but that's very additional and extra. When you chill water, it becomes humified, right? It becomes humified. So when you add chilled water, this chilled water will humify the atmospheric water, and this atmospheric water will be added to the actual mixture. So the mass will be deviated, right? Because if you put the chilled water, the chilled water will humify the water vapors in the atmosphere, and this humified water vapor will be added to the mixture. That will deviate the mass of the mixture. Can happen, but that is very extra. Yes. Yeah, those two can be the best explanation. Right? Think about it and address it. Right. So come to the next one. Bimetallic strip can be cited as one example of a useful application of linear expansion in everyday life. Right. Alpha A is given 5 into 10 to the power minus 5. Alpha B is given 4 into 10 to the power minus 5. For the two expansion of strips A and B. If the temperature of the above bimetallic strip is increased, draw the shape of the bimetallic strip corresponding to the temperature. So if the temperature was increased, the one which expands more will become the outer circumference, because the outer circumference is always larger. The one becomes expand less will become the inner circumference, because the inner circumference is always less than the outer circumference of a circle, right? So like if you compare which one has a higher expansion, that is B. The expansion of B is higher, which means B should be the outer circumference and the A should be the inner circumference. Therefore, A and B, if you take A and B, is something like this. This is A, and this is B. Because A is B is more expandable than A, right? Isn't it? A should be the outer, right? Is it? A should be the outer one because 5 is greater than 4, isn't it? 5 is greater than 4. So it's the other way around. The other way around. Is A, B. Because A expands more, B expands. It will be like this. Mention 2 cases where biometric strip is used in practice. Iron, clothing iron. Yes. Switches. Some switches have this biometric strips. Right. If the length of biometric strip is 1 L is 2 meters, find the increase in the length of each metallic strip separately when its temperature is heated to 32, 50 degrees. So A, they're asking the length of, find the increase in length. Increase in length. That is delta L. Is increase in length. Yeah. Not the final length. Increase in length is delta L. It's a delta L equals L naught alpha delta T. It's 1 meter initial. The expansivity of A is 5 into 10 to the power minus 5. Is 5 into 10 to the power minus 5. And the temperature difference is 30 to 50 is 20. So this becomes 100. 100 into 10 to the power minus 5 is minus 3 meters, which is 1 millimeter. If I take B, same equation, delta L equals L naught or delta theta. Initial length is 1 meter. Expansivity is 4 into 10 to the power minus 5, and the temperature difference is 20. 20 into 4 is 80, right? So it's 0.8 into 10 to the power minus 3. That's basically 0.8 millimeters of expansion. Right. Okay, so that's the end of the structured essay. Yasiru, would you want me to discuss the essay? Like bit of it නැති scene පොඩි සීතල ගතියක් තියෙනවා. If it isn't very difficult, shall I stop it for today? I think the essay part is really easy as I say this. Fine, so thank you. Yes, sir. I think the essay part is like really easy. Not like I don't see any very difficult questions, and if you have any like thing difficult to answer, we'll discuss again. I want to finish biochemistry. I think we have finished the paper production. Did we? If we didn't finish the paper production, I want to finish paper production and biochemistry tomorrow. And those are the like potty parts. We'll finish it tomorrow. So then the IT should be started as well. So from next week onwards, like we are starting ICT. First we can finish it. Yeah, that's the plan. So shall I wind off? Wind off.